Hi, welcome back to the part 3 of this chapter on complex number. So yesterday we sort of looked at how to solve some equalities of complex number, and we basically done this particular proof. So now we'll be looking at some polynomials. So basically it will be on solving equations. So particularly we will focus on polynomials. Okay, so early in this chapter, basically I discussed the quadratic equation. So we all know that for quadratic equation, the general form can be written as ax squared plus bx plus c equals to 0. And we also know that the solution for this quadratic equation in general looks like this. So b squared minus 4ac is what we call as discriminants. And we also know that from previous chapters, when b squared minus 4ac is smaller than 0, then previously we said that this has no real solutions. When b squared minus 4ac equals to 0, we say that this has two real and equal roots or solutions. When b squared minus 4ac greater than 0, we say that you have two real and distinct roots. So these are what we learned previously. So now let's look at this more carefully, especially on the first condition, which is when b squared minus 4ac is smaller than 0. So when you look at this particular condition, when b squared minus 4ac is smaller than 0, basically it means that your b squared minus 4ac is equal to some negative number. Right? So then you can transform this solution of your polynomial into something like this. So you know that b squared minus 4ac is smaller than 0. We are just looking at the first condition. So you can factorize out the minus sign. And when it happens, then basically you have a positive number. So basically over here my assumption is that b squared minus 4ac is negative. So then after that, what you can do is that you write back. So 4ac minus b squared will become a positive number because you already factorize out the negative sign. And square root of negative 1 is equals to I, which I write it here. Okay, so if you write it more carefully, you'll find that this particular part, Rather, this whole thing will be just x plus or minus yi. So whereby your x will be equals to minus b over 2a. Your y will be equals to square root of 4ac minus b squared over 2a. So this is conjugate pair because x plus yi. So let's say if you have z equals to x plus iy, then the conjugate will be x minus iy. Okay, so you can see that whenever you don't have any real solutions, you always form a complex conjugate pair. So therefore we can update this particular rule, this one here, to say that when b squared minus 4ac is smaller than 0, what you actually have is two complex conjugate pair. Sorry, that's a little bit confusing. It's a complex conjugate pair, or you can say it's a two complex roots. A pair basically means you have two roots. So when you say that you have two complex roots, it's not specific enough because one of the root has to be the complex conjugate of the other one, which is shown here. So if you draw the quadratic equation again, this is when b squared minus 4ac greater than 0. You have two real roots. When b squared minus 4ac equals to 0, you have two equal real roots. That's why you only intercept your x-axis once. And when your b squared minus 4ac is smaller than 0, there's no intersection. But it's actually not true because the intersection happens at a complex plane, which you can't see. So that's the update for quadratic equation. From now on, you need to use this particular updated rules for b squared minus 4ac smaller than 0. So what happens with your cubic equation? Basically for cubic equation, what you have is ax power 3 bx squared cx d equal to 0. So in this particular case, what you must take note is you at least have one real root. There's no reason to study, I mean technically speaking, you have a general solution for the cubic equations, but there's no need for you to do that. You can look at it graphically speaking. So cubic equations basically looks like this. So it doesn't matter how you draw it, whether your a is greater than 0 or your a is smaller than 0. It doesn't matter how you draw it. You always have at least one intersection points. So meaning that at least you must have one real roots. So that is the first point for cubic equations. The second point is that whenever you have complex roots, it must come in conjugate pairs. So like these two examples, basically you have one real root and one complex conjugate pair. Because the intersection of the other 2 points are happening in the complex plane, right? So that's why in this particular case, you have one real root and one complex conjugate pair. Otherwise, you will have 3 real roots. So what are the possible cases for these 3 real roots? Sorry. Either you have something like this, which means that one root is different from the other 2. So you have 2 equal roots. Sorry, I should stress that this is real roots. And then another one real root, which is different from the other 2. You can either have these cases or this. So in this case, you have 3 distinct real roots. So these are the possible cases for cubic equation. You must have at least one real root, and if let's say you only have one real root, the other 2 has to be complex conjugate pair, or you have 3 real roots. It doesn't matter whether 2 of them are equal or the 3 of them are different. So these are the possible cases. So now let's look at quadratic equation, which means that you have ax power 4, bx power 3, cx squared, dx e equals to 0. So you can also look at it graphically speaking. Quadratic equation basically looks like this. So if you have something like this, then it means that you have 4 real roots. Of course, you can also have something like this. So the left case will be 4 distinct real roots. This will be 2 distinct real roots, and 2 of them will be, let's say, lambda 1, the other 2 will be lambda 2. So let's say this is lambda 1, this should be lambda 2. Or you can also have something like this. So then you have 3 distinct roots. So let's say this is lambda 1, this is lambda 2, and lambda 3 equals to lambda 4. So 2 of them are equal, the other 2 will be different. So there are a lot of possible configurations. So in this case, you just state that there are 4 real roots. So the other possible cases will be having 2 real roots. Whether they are the same or not, it doesn't matter. You know that there are 2 real roots and you have 1 conjugate pair. So the possible cases can look like this. So you have lambda 1 and lambda 2 being the real ones, and then the imaginary one, you can't see it over here. Lastly, you can also have 2 complex conjugate pair. So perhaps I should write complex. So in this case, then it doesn't intersect your x-axis at all. So these are the possible cases for quadratic equation. And you can extend this particular set of ideas to whatever polynomials of power n. So basically, the meaning is the same. So the take-home message over here is that whenever you have complex roots, it always comes in pair. So that's what we call as the complex conjugate pair. Okay, so let's look at perhaps one example of finding the roots. So let's say you have fz equals to z power 4 minus z power 3 plus 20z squared minus 16z plus 64. So you are also given that this particular quadratic equation can be broken down into z squared plus a multiplied with z squared plus bz plus 4. And you want to solve when fz equals to 0. So the easiest way for you to do it is to start from what is already given. So you need to expand this and find out what is a and b. So then you just expand this, you get z power 4 plus bz power 3 plus 4z squared plus az squared plus abz plus 4a. So this has to be equals to z power 4 minus z power 3 plus 20z squared minus 16z plus 64. So by comparison, you can already see that over here there's no square, equals to minus 1. The next comparison is over here, 4a equals to 64, or a will be equals to 16. So now you want to solve for fz equals to 0. So z squared plus 16 multiplied with z squared minus z plus 4 equals to 0. So let's look at the first part. Z squared plus 16 equals to 0. So z squared will be minus 16. So square root it, you get 4i. Sorry, please remember the plus or minus because of the square root. So the other one would be z squared minus z plus 4 equals to 0. So you can test out b squared minus 4ac. You definitely find that this is smaller than 0. So you can directly use the formula 1 plus or minus square root of b squared minus 4ac divided by 2a. So this is 1 plus or minus square root of minus 15 over 2. So finally what you can write is 1 over 2 plus or minus square root of 15 over 2i. So this plus or minus contributes to what we call as the complex conjugate pair. So there's one particular instances of how you would make use of the information that you have on all these different powers of polynomials to find the solutions, especially the complex solutions. Okay, so after looking at this particular example, the next thing that we want to define is the square root of a complex number. Really, there are two ways to do it. so I will show both ways, and then I will also show how they are equal. So basically speaking, if let's say you have let's say you have a complex number, let u equals to a plus bi. So you want to find the square root of u. So the easier way for us to do is to define. So the first step is to define another complex number, which we call z equals to x plus iy. And then we also say that z equals to square root u. Essentially what we are doing over here is that we define another complex number and then let that particular complex number, which is written as z, to be equals to the square root of u. Then we compare both sides. So since z equals to square root of u, so z squared will be equals to u, right? So then the next step is to square your z. So x plus iy, you square it, equals to a plus bi. So then you have x squared plus 2xyi plus y squared I squared equals to a plus bi. And because of this, I squared becomes minus 1. So in the end, you have x squared minus y squared plus 2xyi equals to a plus bi. So then the third step is to compare the real and the imaginary part. Okay, so let me just state that this is the method, the first method. Method 1. So this is a general procedure. Later on we will look at examples. So then you're comparing the real and the imaginary parts. So x squared minus y squared will be equals to a. So this will be your first equation. Second equation, 2xy will be equals to b. So then what you need to do is to substitute either x or y from equation 2 into 1. So let's name this the fourth step, because at this point you need to look at examples. So basically what you need to do next is to substitute from the second equation into the first equation, either x or y, and then solve the quadratic equation. And find what is x and y. So that's what you need to do, roughly speaking, for the first method. The second method is not covered in the textbook, but I think in some sense it is a lot easier and it makes more sense, honestly speaking. So the idea is that you have u equals to a plus bi. So from the previous sections, we also know that this can be written as, let's say, r e power I, let's say 5. The idea is to make use of the polar form to find the square root. So what you would need to do is the same thing basically. So you need to find the square root of u. So the first step, of course, you still need to define, let's say z equals to, let's use as r e I theta. So this is what you need to define. Define z equals to r e I theta, and then you let z equals to the square root of u. So then z square will be equals to u. And because you write it in a polar form, it's a lot easier for you to write down what is z squared. So basically this is r e I theta square it equals to s e I phi. So this will be r square e I 2 theta equals to s e I phi. So then by comparison, r square will be equals to s, or r equals to the square root of s. In this case, you don't need to write down the negative part, because remember that this has to be positive. Remember from the previous video. So the definition of your r basically is over here. So r equals to square root of x squared plus y squared. This is by definition, and it has to be always positive. So that's why you don't need to put the minus sign. So then, there you go. You find out your r. But to find your angle theta, you need to be a little bit careful. So by definition, we know that the principal argument is given by minus pi to pi. So therefore, when you define this particular angle, you need to be careful. You need to add or minus 2 pi multiplied with some number L. So what is that L definition? That L comes from 0, 1, 2, and so on until n minus 1. And what is the meaning of n? So n is the power of your roots. So in this case, you are square rooting it. So it means your n equals to 2. So meaning that when you want to find the angle, you need to use this particular formula. And then your L start from 0, and then you need to do 0 and 1. So why do you need to do this particular part? The reason being, let's say this is your original complex number, which is denoted by u. So when you square root it, what you are essentially doing is half the angle when you do the square root. But the thing is, your principal argument always ranges from minus pi to pi. If you halve your angle, then it means that you only will from minus pi over 2 to pi over 2. So in this particular case, So, okay, so originally this is your principal argument. And if you square root it, essentially what you are doing is something like this. And this is not the definition of principal arguments. So meaning that you are missing out the other part of the solution because you are shrinking down your principal argument, the range of your principal argument. So in order to counter this kind of effects, basically what you need to do is to multiply the whole thing by 2 so that when you look at your solution, for example, when you divide everything by 2, then you're still getting back your original principal argument. So the multiplication by 2, or over here you plus or minus 2 pi times L, basically is for you to counter this particular effect. So let's look at some examples. So basically you just need to rely on these two equations and you can directly find out what is the square root of a complex number, or even up to the n root of a complex number. So in this case, I do think that the second method is a lot easier comparing with the first method. But let's look at some examples. So example, find the square root of minus 2 minus 2 root 3i. So let's do it by the first method. So what you need to do is to let u equals to minus 2 minus 2 root 3i, and then define z equals to x plus iy, and z is equals to square root of u. So z square will be equals to u. So previously we already calculated z square to be x square minus y square plus 2xyi, and u is minus 2 root 3i. So x square minus y square will be equals to minus 2. This is the first equation. 2xy equals to minus 2 square root 3. So let's simplify this first. So y equals to minus root 3 over x. So this will be our second equation. Okay, so now what we need to do is to substitute equation 2 into equation 1. So you have x squared minus y squared. Once you square this whole thing, you get 3 over x squared. So this is equals to minus 2. So multiply everything with x squared. So you have x power 4 minus 3 equals to minus 2x squared. So you have x power 4 plus with 2x squared minus 3 equals to 0. So now you can factorize this as if this is a quadratic equation. X power 4 minus 3, 2x squared plus minus. So you have 3 over here, 1 over here. So what you have is x squared plus 3, x squared minus 1 equals to 0. So this is where you need to be careful, because you can either have x squared plus 3 equals to 0, or x squared minus 1 equals to 0. So from your definition, z equals to x plus iy, this has to be real. Y also has to be real. So meaning that you have to reject this part of the solution because this will give you x to be a complex number. So then you can only proceed with the second equation. So x will be equals to plus or minus 1. So finally, what you have for y will be equals to minus root 3 over x. Therefore, when x is positive, you have minus root 3. When x is negative, you have plus root 3. So meaning that if your x is plus or minus 1, your y will be minus plus root 3. So finally, write down your complete solution. U can either be 1 minus root 3i, or u can be minus 1 plus root 3i. Okay, so this is the solution from method 1. Let's look at how we would do it with method 2. So remember that what we would, sorry, this is not u, but square root of u. So remember what we need to do first. We need to define your u to be in the polar form. So if u is equals to minus 2 root 3i, so the modulus of u would be 4 plus 12, which is 4. The argument of u would be the inverse tangent of 2 root 3 divided by 2. So this is in your third quadrant, meaning your angle has to be defined negatively. So what you will need to do is to put a minus sign to count to sort of like define the direction of your angle, and then pi minus pi over 3. So pi over 3 basically is coming from inverse tangent of root 3. Okay, so this gives you minus 2 pi over 3 radian. Therefore, your equation can be rewritten as 4e to the power of minus 2 pi over 3i. Okay, so now let's define z to be REI theta. That's what we define, right? Yep. So let's define z to be REI theta, and z equals to square root of u. So this means that your z squared equals to u. So z squared will be r squared EI 2 theta equals to u, which is 4e minus 2 pi over 3i. So r squared equals to 4. This means that r will be equals to 2. Only take the positive side. The other one, 2 theta equals to minus 2 pi over 3. Remember to put that plus or minus 2 pi multiplied with L. So L can be 0 or 1 because you only count up to n minus 1. So n is 2, 2 minus 1 is 1. So L only counts from 0 to 1. So now what are the possible solutions? 2 theta equals to minus 2 pi over 3 when L equals to 0. Or 2 theta equals to minus 2 pi over 3 plus 2 pi So why don't I do the minus? Because remember just now, what I would need to do is to look at the 2 theta from minus 2 pi to 2 pi. So if you do it, if let's say you are using the minus 1, so minus 2 pi minus 2 pi over 3, this definitely exceeds your lower limit. That's why you don't need to consider this. So here I write down why don't you need to consider this. It's exactly because of this particular range. So from the left hand side, theta will be equals to minus pi over 3. And then the other one will be 2 theta equals to, sorry, I think I need to calculate that a bit. 4 pi over 3. So theta will be 2 pi over 3. So finally, write down your solution. Square root of u or z will be equals to 2 e minus pi over 3I or 2e 2 pi over 3I. So if you want to convince yourself that this is the same solution as the method 1, what you can do is to expand this. So this is basically cos minus pi over 3 plus I sine minus pi over 3, or the other solution will be 2 cos 2 pi over 3 plus I sine 2 pi over 3. So calculate this number. In the end, you will get 1 minus root 3I minus 1 plus root 3I, which is the same as the solution above. So that's how to do it with both methods. Now let's look at some other examples. Find the square roots of. So let's look at A. So u is given by half e pi over 2 I. So if you were to do the method 1 case, you will need to convert this. So this is cos pi over 2 plus I sine pi over 2. So in the end, this is 0, so you have half I. So then you just proceed to go through what you need to do for method 1, rejecting the parts that gives you imaginary numbers and so on. And then finally you will find the solution. But what I would want to focus on for this particular example is to use method 2. Because they already give you the polar form, why not using it? So you let z equals to r e I theta, and this will be the square root of u. So r square e I 2 theta will be equals to u. Okay, so r square is 1 over 2. So this means that your r would be square root 2 over 2. 2 theta equals to pi pi over 2. Remember, you need to either plus or minus 2 pi times L. So L will be given by 0 and 1. So always remember that your theta ranges from minus 2 pi to 2 pi. Okay? So now, your 2 theta can either be pi over 2, which happens when L equals 0, or it can also be pi over 2. So you definitely can't do the plus, because if you do the plus, it will exceed the upper limit. So you can only do the minus. So theta either is pi over 4 or minus 3 pi over 4. So finally, your square root of u would be given by square root 2 over 2 ei pi over 4, or square root 2 over 2 ei minus 3 pi over 4. So finally, if you want to convert it back to the a plus bi form, you can do that with this particular set of solutions. So let's look at one more example. So this particular example looks like this. Part B. So let u to be 7 plus 6 root 2i. So because they give you in this form, it'll be more natural if you use method 1. Of course, you can try method 2. So that will be left for you to do it. So you let z to be x plus iy and z squared to be u. So x squared minus y squared plus 2xyi equals to 7 plus 6 root 2i. So x squared minus y squared equals to 7. This is the first equation. Second equation, 2xy equals to 6 root 2. So y will be equals to 3 root 2 over x. So now substituting equation, 2 into 1. What you would get is x squared minus y squared, 18 over x squared equals to 7. Or x power 4 minus 7x squared minus 18 equals to 0. So let's do this. So this would be 2, 9. So you have minus 9x squared, 2x squared. So you have x squared plus 2, x squared minus 9 equals to 0. So as usual, this part will be rejected because x cannot be complex. So you have x squared minus 9 equals to 0, or x equals to plus or minus 3. So when x equals to plus or minus 3, you look back at your y. Y would be equals to plus or minus root 2. Therefore, your square root of u would be 3 plus root 2i. The other one would be minus 3 minus root 2i. So that's how you find the square root of a complex number. So we'll stop here for today. Thank you. See you tomorrow.